Okay, okay. Hey, should I start? Umaya Lakshmi? Okay. So let me share my screen. Okay, so let's go to this structural induction and strong induction. You had some doubts, right? Okay. Hello, am I audible? Can somebody? Okay, I can't
Yes.
see the meeting thing, so just let me know. Okay. So for the strong induction, what happens is, let's say I have I is equal to 1 to n. Okay, I is equal to 1 to n. And what I want to prove is that P of some theorem, some proof, something, some theorem, something is happening for this set of values. Okay, so in induction, what we are trying to do is we show that, okay, this is true for I is equal to 1. When I becomes 1, this happens. Whatever the x thing that is supposed to happen, that is happening. Then we show that suppose this is happening for some random value of n, let's say k, between 1 to n, this is happening, then the next thing will also happen. If this happens, then this happens. Okay, so this is what induction is about. So what happens is, what is the proof here is, if I is equal to 1, that means it is true for I is equal to 1, which is the base case, the base value, for whatever is the base value. It is not always 1. Okay, it may be the case that your input set will be from -5 to +5. In that case, you will have to show that it holds true, the theorem holds true for when I k is, when n is equal to -5, or the value will be, when your variable is set to -5, then the function holds true. Okay, so that is what you have is the base case. So in the base case, you have to show for the minimum value in the domain, whatever the domain is, in the for the minimum value of the domain, you have to show that this holds true. So now once this holds true, you have already shown, you also show that if one value, for one particular value, it holds true, then it will also hold true for the next successive value. Okay, so if it is true for k, then it will be true for k plus 1. So now because you have already proven this, what will happen is, because you already know that I is equal to 1 is true, so I is equal to 2 will also be true. Similarly, since I is equal to 2 is true, I is equal to 3 will also be true. For I is equal to 3, it will be true. Okay, so similarly, this is what the proof goes on. So but what happens with strong induction is, we don't assume that, we don't just pick some random value and say that, hey, if it is true for this random value, then it will be true for the next value as well. What we are going to show is that with the strong induction, you have to show that if it is true for I to k, for every value of I to k, let's say that I am just picking some random value k, and I'm assuming that it is true for I is equal to 1, it is true for I is equal to 2, it is true for I is equal to 3, up to it is true for every value from I is equal to 1 to k, then it will be true for I is equal to k plus 1. Okay, so now why this thing holds true is, suppose I am saying that I already know that I is equal to 1 is true. Because I is equal to 1 is true, there are no other values between I is equal to 1 and 2. Okay, so because I is equal to 1 is true, I is equal to 2 will also be true. So now we already know that I is equal to 1 is true, I is equal to 2 is already true. So because of the, based on this principle, principle of strong induction, I is equal to 1 is true, I is equal to 2 is true. So I is equal to 3 will also be true. Now since all three of these are true, I is equal to 4 will also be true. What I mean by I is equal to 4, it will be true is when I becomes equal to 4, whatever proof you are trying to prove using the variable I, it will hold true. Okay, the theorem holds true. Okay, so this is the principle of strong induction. And then for structural induction is basically you have a structure. This is just a bunch of values, right? You have a bunch of values and you just have to see that the next value comes up. Okay, in the structural induction you have a structure. For example, a tree structure. There is a root node. Okay, and then it is having two children. So now notice that this is the root for the entire tree, right? This is the root for this entire tree. But now if I remove this root, what will happen? This becomes the root for this part, and this becomes the root for this part of the tree. This part of the tree, this is the root, right? So now there is some kind of a systematic consecutiveness in that, right? Because here we have a root, then there is something as child, and this child is the root of something else. This child is the root of something else, and then you combine them into the root of one thing, and then you combine them and you get one node, and this node is the root of something else. Now notice that I am having two trees. Okay, this is the root of something. This is the root of another tree. Let's say R2. This is R1. Okay. And then I am going to add a node over here. I call it R. And now this node and becomes the parent of this R1 and R2. Then what happens? My R becomes the root of this entire tree. Recursion kind of a thing, right? There is some form of a level in the tree, in this tree structure. Okay, so in this kind of a structure, if you have some kind of a level, then what you do is you prove it for the bottommost level. Okay, this is one technique. You prove it for one of the bottommost level, then show that this holds true for one some level I is equal for some level L. Okay, whatever theorem you want to prove, so that it holds true for that particular level. And if this condition holds true, that it holds true for this particular level, then it will hold true for its previous level as well. If you prove that, you already know that the leaves are true. It has been it is satisfied for the leaves. So you know that if it is happening for one level, then it is also happening for the previous level. Since the leaves are at the lowest level, you can show that using this particular proof, you can show that it will also be true for its previous levels. Okay. Now, since this level L minus 1, the level H minus 1, okay, let's say height, this is the height, total number of levels is H, okay. So then this will be H minus 1th level. Then similarly, it will be because H minus 1th level is true, it will be true for H minus 2th level, and so on, okay. Now, similarly, you can do it in a top-down manner also. You show that this holds true for the root. Here, the difference is if you do in a top-down manner, the difference will be for the root, it will just be like one value. The base case will have exactly one value. You don't have to solve the, you don't have to prove the base case for every leaf in the tree. But for some scenarios, it will be easier to show that it is true for every leaf in the tree. Okay, so that's why it will be easier to show that it will be easier to go from a bottom up approach, but for some cases it will be easier to go from a top down approach. So you go start from the root of the tree, you show that this happens for at the root R2, then you show that it happens for level L. If this theorem holds true for level L, then you prove that if the theorem holds for level L, then it will also be true. The theorem will also hold true for level L by L plus 1. So we already know that level L equals to 0 or L equals to 1. The root note, the level at which the root is present, level L equals to 0. This holds true. So since it holds at level L equals to 0, from your induction hypothesis, you can say that it also holds for L equals to 1, the level L equals to 1. If it holds at level L equals to 1, then it will happen for L equals to 2 as well, and so on. This is structural induction. Any doubts in the concepts. This is basically the concepts of structural induction and uh, strong induction and the basic principles of mathematical induction. So apart from this, if you have any specific doubts, then let me know. Otherwise, we'll go to week 4 content.
Yeah, ma'am, in week 4 itself, there are some questions regarding strong induction, which involves inequalities.
That is week 3 content.
Okay,
Can you please share which one you are talking about? Can you please share your screen and show me which one you are talking about?
wait, I have to open it first.
Yeah, okay.
Okay, ma'am, you continue because I am unable to find it at present. I will share with you in chat.
Okay, cool. Okay, so in week 4, basically the idea is on cardinalities of sets and the topics are cardinality of sets and the recursion. So, cardinality of sets here, basically cardinality of sets. In cardinalities of sets, we have these different types of. Okay, so let's discuss what cardinality of a set is. This so cardinality. So, given a set S, its cardinality is basically the number of elements present in that set. Okay, it is denoted as like this. So if there are 5 elements in set, then in the set S, then mod of S is equal to 5. Okay. So basically, cardinality of a set is the number of elements present in the set. So now there can be different types of sets depending on its cardinality. So finite sets are basically the number of sets which have a finite number of elements. Finite number of elements, you mean it is limited. It can be 100, it can be 1000, it can be 10,000, it can be 100,000, it can be tens of hundreds of thousands, but it is limited. Okay, so that is what finite sets are. Then we have countable sets. Countable sets are where you can count the numbers. Okay, so now you can ask like what is the difference between finite sets and countable sets. So what happens is in let's see if you take like in countable sets you can count. Okay, like A B C D E F G H, you can exactly count the numbers. Okay, but then there are finite sets which basically says that you may not be able to count, but I'm limited. Okay, I have a distinct number of elements, but you may not be able to count. Like for example, uh, let's say this S is equal to there is a name ABC, there is a set 5, then there is a number 5, then there is a space, okay, then there is something else, then there is some 1500, then something else, then something else, and something else. It's just completely random, okay. So, and there are some hundreds of thousands of values here. So now the point is, can you exactly count how many elements are there in the set? For that, what you have to do is you have to look into the element and then count it, right? You put every element side by side and then you count it. But if it is in hundreds of thousands of range, then you won't be able to do that counting. Like you cannot put every element next to each other and then count it. Okay. So what countable sets are, they use some kind of a formula to count the number of elements in the set. Suppose I say S is the set such that the elements in the set start from 1 and go up to 500. Okay, then here you can exactly count the number of elements in the set. You just take 500, subtract by 1 and add by 1. So that will be basically 500 minus 1 plus 1, which is basically 500 elements. So from this itself, you can just use some kind of a formula. You can just count the elements without having to put it next to each other. Okay, so that is what a countable set is. Uncountable is you won't be able to. There is no formula to count uh, this count, you won't be able to count these elements in the set, but then there are infinite sets, which are basically the elements is infinite, like you have minus infinity to plus infinity. So these are basically there are infinite number of elements. Uncountable sets are you won't be able to count them, and generally when we use the term uncountable, generally it is used to denote infinite sets only. Okay, this is a very vague example. Okay, so these are the four different types of sets. Then yeah, then the ma'am I think had provided several examples. This is the set of natural numbers is an infinite set. So there are infinite sets, finite sets. Then we have countable sets and uncountable sets. Okay, so I missed one point. So here I said that this is hundreds of thousands. Even if it's hundreds of thousands, then you will be having a number. But if there are infinite such values, then you won't be able to count the number of values, right? So that's why it is a uncountable set. Okay. So this is a valid example, provided you don't know how many elements are there in the set, and it can be and it can go up to infinite, then you won't be able to count because there is no specific formula to count these values. Okay, so that's why it is uncountable. Countable is it, if it is finite, then you can just put them, stack the elements on top of each other, and then you can count the elements. When I said hundreds of thousands, I meant an infinite level of numbers, an infinite, very large number of very large number of elements in the set. Okay. So countable, if it is finite, then it will be basically you can stack the numbers on elements on top of each other and next to each other, and you can count it. But uncountable is you won't be able to do that. Okay, that's the difference, and there are different examples on what are countable sets and what are uncountable sets. The set of rational numbers. This is basically some trivial, not some trivial, but this is something you can just remember the set of natural numbers, the set of integers, the set of rational numbers. Okay, all of these are countable sets, but the set of real numbers is uncountable. Okay, so the proof is actually given here. Ma'am has provided the proofs and everything, so you can look into the proofs and the lecture videos. So now, obviously, if you are having two countable sets, suppose there is a countable set and you take a subset of a countable set, then it will obviously still be countable. Okay, because it is finite. There are limited number of elements. You can count the number of elements in the set. So using a similar formula, you should be able to find the you should be able to count the number of elements in its subset also. Uncountable sets, its superset will also be uncountable because you already have uncountable, you already cannot count it, and now you are adding some more elements to it, then then it will become uncountable. Okay, so these are the some theorems. Okay, there are two countable sets A and B. If you take a union of that, it will still be countable. These are some properties of countable and uncountable sets. So you take A union B, then it will still be countable. See, you can count the elements. So how do you know if you can count why it will be true? A very intuitive proof is basically you count the elements in A, you count the elements of B, and then you just sum it up. Okay, it will be maximum will be that. Okay, so that's why A and B, if they are countable, then A union B will also be countable. Okay, similarly, A intersection B will also be countable. Anyways, A intersection B is a subset of the original set, so it will be original countable set, so it will still be countable. Okay. Then comes union of countable sets, infinite sets and countable sets. So every infinite set contains a countably infinite set. So this is basically it's a proof saying that if you have an infinite set, then maybe there is a subset of that infinite set uh, containing a countably infinite set. Okay. So this is about countable, sorry, cardinality. Then there is recursion. In recursion, it's basically the same thing that you have learned in recursion from your PDSA courses and everything. Recursion is basically what happens is you are calling the same function again and again. Okay, you are proving something for the base case. You know where to quit the function, where to stop the function. You know the base case is holding true, and then you are calling the same function again and again. Okay, so recursion here also it's the exact same thing. What it is basically you are defining an object or you're calling an object, but this is just a mathematical definition. It's the same thing, same concept, but here we are having some mathematical definitions. Okay, so we want to define recursion for, we have seen recursion in PDSA courses and other courses for functions, right? So for functions, what we used to do, there was some function which used to take a parameter, and then we used to call this function with different values of the parameters again and again. Like for example, we want to compute for f of 10, then inside this we will be calling, based on some condition, we will be calling x minus 1 if it is x. Okay, and then it will keep on repeating that, right? So this is what function was. We started with f of 10, then we call f of 9, then we do f of 8. From f of 9 we call f of 8. From f of 8, we call f of 7 and so on. Okay, so recursion is basically you keep on calling the same function again and again with smaller or a different value, smaller values or different values, and you know where to end, right? So that is what here recursion for functions is also in the mathematical terms. You have what is the value for f of 0. Let's say f of 0 is equal to 5. Okay, and we define f of x plus 1 is equal to 2 times f of x. Okay, so now we want to compute f of 10. Then what will you do? You do 2 times f of x is basically 10 minus 1, which is 9. Okay, f of 9 is again, uh, f of 9 is again 2 times f of 8. Okay, similarly, f of 8 is again 2 into 2 into f of 8 will again be written as 2, can be written as 2 times f of 7. Okay, and so on. So this will give you 2 to the power 10 times f of 0. Okay, so this will be basically 5 times 2 to the power 10. So this is what a recursion is. This is what a recursion is for functions. Okay. Now coming for sets. For sets also you can define similarly. Let's say a set is defined as. Let's see an example. Sets. Okay. Okay. So for sets, let's say I'm claiming that 3 is an element of set. Okay, I'm claiming that 3 is an element of set. Then I'm claiming if x is an element of set and y is an element of set, then x plus y is also an element of the set. Then can you find out what the set will look like? So I have my set. I know that 3 is an element of the set. So if x is an element of set, y is an element of set. So like now I'm going to set 3, both x and y is equal to 3. Okay. So now if x is equal to 3, then 3 is an element of set. So this is true. If y is equal to 3, then this is true. So now we will be having x plus y will be equals to will be in S. So x plus y equals to 6, so 6 will also be in S. The next case we will be having
Hello,
x can,
ma'am.
yes, yes,
Ma'am, my question is here. We have assumed that 3 belongs to S, right? Now,
yeah.
three is
We
only.
don't assume that. We are not assuming that. We are given a base case. Just like for recursive functions, you have a base case. You know where to stop. This is the base case.
Means we for base case we have been given like 3 belongs to S.
Yes.
Now X belongs to S and Y belongs to S. Means Y cannot can be X and Y can be any number, right? Can be
Yes,
any.
it can be any number. Yes, x and y can be 1, 2, 3, 4. The domain is basically your set of integers or whatever. The domain, if the domain is given to you, then it will be basically your set of integers here. Let's consider the domain is a set of integers. So your x and y both can be your integers. So x can be 1, y can be 1, y can be 2. But in this case, x is not in S, y is not in S. At least we don't know if it is in S or not. Okay. So we don't know if x and y are in S or not. So we can't start with them. We don't know. We can't assume that it is in S. Now I'm going to do x is equal to 2, y is equal to 3. Y is in S, but x is not in S. So I don't know if x is in S or not. So now let's go to the next part. Let's go to x is equal to 3, y is equal to 3. If x is equal to 3, y is equal to 3, then this condition is getting satisfied, right?
Okay.
So I
So
can
so
safely claim
whenever
that 6
only,
is also in S. Yeah.
so whenever only one element is given, we just have to means increase it by that, like 3, 6,
Yes, yes.
9, like that
No,
only.
not 9. See, that is the point here. You can't just have 9. So x can be 3, y can be 6, then you will get 9 is in S. Okay. But what if x is equal to 6 and y is equal to 6?
Okay.
Then you will have 12 also. If x is equal to 6, y is equal to 9, then you will get 15. Okay. So you have to check also.
Okay. Understood.
Okay. Yeah. So then we can have multiple conditions also. 3 is in S, 4 is in S. If x is in S, then x plus 2 is in S. Can you tell me what will be the set? You have 3, you have 4. We already know that. Now, if x is in S, then x plus 2 will also be in S. So, 3 plus 2 will be in S, so 5 is in S. 4 plus 2 will be in S, so 6 will be in S. 5 plus 2 will be in S, so 7 will be in S. 6 plus 2 will be in S, so 8 will be in S, and so on. Getting the concept? Is this clear?
Yes, ma'am.
Hello? Okay. So, this is about sets. Then structures. Okay, so structures basically similarly. Oh, structural induction is in week 4. Okay, okay. I covered that for. I thought it was in week 3. Okay, I have actually explained structural induction, right? So using
Yes.
that structural induction, you can so for recursion also. Similarly, you can do for recursion also. Like you have the root, you show something for this is your base case. You show something happening for the root, then you show because it is happening for the root. Use the value of the root to compute the same value for the uh, leaves. Sorry, for its children as well. Now use these values to compute the same for its children as well. Okay. So this is basically structural, same induction principle, but here you are applying the recursion. Okay, structural recursion. Okay, anything else? Let me just check if anything else is there. Okay, no, this is done actually. Okay, so the content is covered. If you guys have any doubts, you were sharing some doubts, right? You were having some doubts, right? Maybe you can share it. We can
Yes,
discuss
ma'am. That
together.
in recursion there is one proof using strong induction, like Fibonacci sequence.
Okay.
Could you please once do that? Like
Okay. Let me see.
it was there in the slide that we just
In
posted.
the slides itself, okay. Which one?
In the ele- uh, recursion,
Let's close.
recursive definition of set slide. Uh,
Set of strings. This one? No. Okay, you want Fibonacci numbers, right?
yeah, Fibonacci sequence using strong induction.
Okay, this is not Fibonacci numbers. You don't have, you're not proving Fibonacci numbers using strong induction. This is a property of Fibonacci numbers that you are proving using strong induction. Okay, what this says is you take the what are Fibonacci numbers? We have different Fibonacci numbers, right? Our Fibonacci numbers are like 1, then 1. We can start with 0 as well. 0, 1, 1, 2, 3, 5, 8, 13, 13, 21, and so on, right? So now what this Fibonacci numbers is saying is this is the first Fibonacci. This is, let's say this is the zeroth Fibonacci number. This is the zeroth Fibonacci number or first Fibonacci. Okay, I don't know if they're taking this is the zero. Let's take this is the zeroth Fibonacci number. Okay. So this is the first Fibonacci number, this is the second Fibonacci number, and so on. Okay. So for this case, n is equal to 1. So when n is equal
No,
to
your
1, your
screen
fn
is
is
not
equal to,
shared.
oh, sorry. Visible now? Is it visible?
Yes, ma'am.
Okay. So, 0, 1, 1, 2, 3, this is our Fibonacci numbers, right? So now this is, let's say this is our first Fibonacci number. This is, let's say we are taking, this is the zeroth Fibonacci number, okay? Let's not take this, okay? Let's begin with 1. So this is our first Fibonacci number. This is our second Fibonacci number. So n is equal to 1 for this case, n is equal to 2 for this case. So basically our f1 is equal to 1, okay, and f2 is equal to 1, f3 is equal to 2, third Fibonacci number is 2, okay, fourth Fibonacci number is 3, fifth Fibonacci number is 5, and so on. Okay, so this is how the notation is. So what that proof is saying is for n greater than 3, hang on. Okay, so for n greater than 3, greater than equal to 3, okay, we have if n is greater than equal to 3, then our fn will be greater than alpha n minus 2. So this is basically alpha is equal to 1 plus root 5 divided by 2. Okay, so this is basically the what the theorem is, and it's just saying that you have to prove it. It's not asking you to count the Fibonacci numbers. It is not asking you to find the Fibonacci numbers or anything. This is just a property of the Fibonacci numbers that they are proving via this. Okay, so let's see the proof. Okay, Pn will be the given statement. Alpha less than 2 is equal to f3. And alpha square is equal to 3 plus F3. Okay, so basis step should start from your 3, right? Our basis step will start from 3. So Fn, which is basically F3 for the basis, for the base case, okay? Our F3 is equal to what? Uh, According to this proof, F3 should be greater than alpha times 3 minus 2, which is equal to alpha times 1. This is our basis. This is what we have to prove for our basis, right? So now F3 is equal to what? F3 is equal to 2, right? Yeah, F3 is equal to 2. So we have F3 is equal to 2. Alpha to the power 3 minus 2 is equal to alpha, which is equal to 1 plus root 5 by 2. And if you solve it, you will know that this is less than 2. Okay, so this is basically saying that alpha is less than F3. Okay, so which also implies that alpha to the power 3 minus 2 is less than F3, which means that your F3 is greater than alpha to the power 3 by 2. This proves your base case. Is this clear? The base case is clear, right?
Yes.
Yeah. So now let's go to the induction hypothesis. So this is using strong induction hypothesis. So what we are going to do is for some value 3 to k. Okay, so we have 3 less than equals to and less than equals to j less than equals to k for every value from 3 to k. So we are going to prove that this should hold true for every n greater than equal to 3, right? So what we're going to do is we are taking some k in between, and I'm assuming that this theorem, this formula holds true for every value from uh, 3 to k. Okay, so for every j, for all j such that your j is less than greater than equal to 3 and less than equal to k, this holds true. So fj, which is the jth Fibonacci number, is greater than alpha n minus 2, right? So now what is the induction proof? How do we prove? What do I have
Alpha
to prove
raised
then?
to j minus 2. It should be j minus 2.
Yeah, sorry. It should be j minus 2. Then what do we have to prove now? We have to prove what? What is the principle of strong induction? If it holds true from some
It should.
particular, from the minimum value to some particular value, then it should also hold true for the next value,
Yes.
right? So what we have to prove here? What will be the next value of j?
4.
Not 4. See, we see that 3 to k it is holding true. This means that this particular statement means that f of 3 is greater than alpha 3 minus 2. F of 4 is greater than alpha 4 minus 2. F of 5 is greater than alpha 5 minus 2. And so on until f of k is greater than alpha k minus 2. This particular statement means this. And all of these are connected by and.
Okay, okay.
Okay, so then what do you have to prove now? What will be the next value? After k, what will come?
K
K
plus
plus
1.
1,
Yes.
right? So we will have to prove what?
So for k plus 1, f sub
Yeah,
k plus 1.
f of k plus 1 should be greater than what?
Alpha raised to k plus 1 minus 2. With k,
Exactly. Okay, so this will be actually equal to alpha to the power k
k
minus
minus
1.
1.
Okay, so we
Yes.
have to prove this. Now let's try to prove it. Okay, so how do we prove it? We have f of k plus 1, right? Can you calculate f of k plus 1? How do you calculate f of k plus 1? It's a Fibonacci number. So what will be the k plus 1 at Fibonacci number? How do you calculate a Fibonacci number at any position? Do you know what Fibonacci numbers are, right?
Yes.
Yeah, so
Like
how do you calculate the k plus 1 at
add
Fibonacci?
last two. Uh,
Last, yeah, so the last two is what? Fk And
Fk minus 1.
exactly, right? So now we know that Fk is greater than alpha k minus 2 from here, right?
Mm-hmm.
This
Yes.
one. And similarly, Fk minus 1 is also greater than alpha k minus 2, sorry, k minus 1 minus 2, which is equal to alpha k minus 3, right?
Yes.
So now I'm going to substitute this here. So my f of k plus 1 equals to f of k plus f of k minus 1. Since both of them are greater than these values, I can just write this is greater than f of k is greater than alpha k minus 2 plus alpha k minus 3. Is this okay?
Yes.
Right. So then this will be equal to what? This value, can you solve it? Alpha to the power k minus 3 times alpha plus 1, right?
Yes.
Yes. So now let's substitute. Let's keep this alpha k minus 3 into alpha plus 1. This will become what? So what was it going to? Okay, so then there was
They
something
have
else.
taken a product, I think.
Somehow they have shown that this is 1 plus, this is what is the value? 1 plus root 5 by 2. Root 5 by 2. This is actually greater than alpha squared. We have to show this much, right? If this is greater than alpha squared, let's say, suppose this is greater than alpha squared, then we will have alpha k minus 3 times alpha squared. This will be greater than this entire thing will be greater than alpha k minus 3 times alpha k minus squared, which is equal to alpha k minus 1, right? Hello.
Yes, yes.
Remaining is we just have to show this part. So we have to show what? 1 plus root 5 divided by 2 is greater than 1 plus root 5 by 2 whole square. This will be 1 plus root 5 into 1 plus root 5 divided by 4. Can you solve this out? Use some calculator or something. 1 plus 5 plus 2 root 5 divided by 4. This will be 6 plus 2 root 5 by 4, which is equal to 3 plus root 5 by 2. Okay, and this is 2 plus 1,
3 plus root 5
3 plus
upon
root 5 by 2. This is again 3 plus root 5 by 2. Okay, so this is equal to. Yeah, it's still holding true. Okay, okay, okay. Okay, let's solve it from here itself. Okay, so this is coming alpha k minus 3 uh, times 2 plus 1 plus root 5 by 2, which is equal to alpha k minus 3 times 3 plus root 5 by 2, and alpha squared is equal to 3 plus root 5 by 2. Okay, so this is equal
yes.
to alpha k minus 3 times alpha squared, which is equal to alpha k minus 3 plus 2, which is equal to alpha k minus 1 to the power k minus 1. Is this okay?
Yes.
Yeah. So basically, this is the proof. So whenever you are facing with some induction or strong induction thing, All you say for this entire subject, no, you just need a lot of practice. You just have to do some practice. You just have to try to solve a bunch of problems, and you'll get there. Okay, you don't have to feel so scared. Anything else you want to discuss? Any other doubts or questions?
No, not as of now.
Okay.
Ma'am, could you please post that slides? Uh,
Slides are not available.
no, not as of now.
Okay. Umaya Lakshmi, you are around. Any idea on what is happening? Yeah, they are saying that they don't have the slides. Okay. Yeah. Uh, any other questions?
No,
Hers and
that's it.
okay. Okay, if there are no other questions, then we can end the meeting here. Mahalakshmi, can you please end stop the recording and the meeting too?